Ever noticed how you blink and it's midnight when you're having a blast, but it feels like time's got arthritis when you're working on homework? Well, this is all due to the enchanting trick of time perception. It's an intriguing phenomenon that molds our experience of time based on different situations. Sometimes moments whiz by like a sports car, at other times they creep like a snail. Incredibly, it's all about how we perceive it. This concept, on a wider and more profound scale, is the foundation of a groundbreaking theory you may be familiar with. Let's delve a little into the theory of relativity. Picture a superhero nestled in the heart of a Swiss patent office, a man of extraordinary intellect, none other than Albert Einstein. The year was 1905, when our hero's superpowers began to truly shine. In the midst of the ordinary, Einstein, a young physicist with the mental prowess of a demigod, found himself captivated by a profound enigma. What would the world look like if I rode on a beam of light? This intrigue about light wasn't new for our protagonist. As a 16-year-old, he'd already imagined himself speeding alongside a beam of light. But while surrounded by the mundane at the patent office, his superhuman intellect began to probe deeper. He hypothesized that if he could match pace with a light wave and ride with it, he should see the wave frozen in space. But this clashed with Maxwell's equations, the backbone of electrodynamics, which professed that light always travels at a constant speed, no matter the observer's motion. This paradox baffled our superhero. But Einstein, with his mental superpowers, wrestled with the problem. And then one day, it struck him like a thunderbolt. The anomaly was not with the light or Maxwell's equations. The real problem was our understanding of time. Einstein, with his vision, proposed that time was not absolute. It could speed up or slow down depending on one's relative motion. This was a radical shift from the conventional understanding of time as a fixed, unvarying entity. He encapsulated these revolutionary ideas in a scientific script titled On the Electrodynamics of Moving Bodies. This heroic feat proposed a new theory, a theory that would transform our comprehension of the universe forever. It proposed that the laws of physics are the consistent for all non-accelerating observers, and that the speed of light is constant regardless of the observer's speed or direction. This, and gentlemen, was the special theory of relativity. A superpower theory born from the mind of our superhero, inspired by a beam of light and honed in a patent office. And fellow beings marked the birth of the theory of relativity. Let's narrate a unique tale about two identical twins, Albert and Isaac. Albert, the more grounded one, chooses stay put on Earth. Isaac, on the other hand, full of curiosity and thirst for adventure, embarks on a space odyssey, breaking barriers and soaring at velocities just under the speed of light. As Isaac propels himself through the cosmic expanse, the mystery of time dilation unfolds. This phenomenon, a cornerstone of Einstein's theory of relativity, makes time crawl for Isaac compared to Albert's pace back on Earth. Sounds confusing? Let's break it down. Einstein's theory of relativity suggests that the faster an object travels, the slower its time will pass compared to a stationary object, all because the speed of light never changes, regardless of one's point of view. Therefore, as Isaac hurtles through space at near light speed, his clock lags behind that of Albert's on Earth. This means that if his journey at such dizzying speeds lasts 5 years by his spaceship's clock, on his return, he would be baffled to find more than 5 years had elapsed on Earth. Isaac would have aged less than Albert. Imagine him being a youthful 55, while Albert, his twin, is already past his 60th birthday. Seems like an intriguing sci-fi plot twist, isn't it? But no, it's an astonishing reality emerging from the theory of relativity. As Isaac rockets around the universe, he's not just a space explorer but a time traveler as well, albeit at a different pace than his brother back home. Thus, time isn't a fixed entity as per our daily perception, but one that bends and alters as per speed and gravity. It's a flexible, shape-shifting dimension that can stretch and contract, twist and turn. In the world of relativity, time is certainly not absolute. Visualize a hefty ball resting on a trampoline and causing a depression around it. This elementary illustration is an excellent introduction to the concept of how gravity warps space-time. The heavy ball, symbolic of a substantial body like a planet or a star, when placed on the trampoline, warps fabric. This is akin to how gravity twists the fabric of space-time. Let's delve a bit deeper into this. If we roll a smaller ball, symbolizing a less massive object along the trampoline's surface, it will naturally gravitate towards the heavier ball. This is not because the heavy ball is actively attracting it, but because the smaller is following the curve the heavy ball created. Similarly, gravity is not a force that pulls objects, but instead, it's the curvature of space-time that directs the course of objects. This notion is central to Einstein's general theory of relativity. It departs from the traditional Newtonian perspective of gravity as a force interacting between two bodies. Instead, Einstein postulated that gravity is the outcome of the distortion of space-time due to mass and energy. Like the heavy ball on the trampoline causing a dip, the Sun, being the largest object our solar system, creates a considerable depression in space-time. The planets, akin to smaller balls, follow the curves created by this dip. They're not being drawn by the Sun, but they're moving along the curvature of space-time created by the Sun. Hence, gravity, according to the general theory of relativity, is not a force pulling objects, but a curvature guiding them. This theory's beauty lies in its simplicity and elegance, offering afresh to understand the universe and the fundamental forces that shape it. So, anytime you're at a planet in the night sky or experience gravity's pull, remember, it's not just a force tugging at you. It's the curvature of space-time directing your course. Therefore, gravity is not a force drawing things, but a curvature leading them. Ever pondered why in the cosmic race light always claims the gold medal? This question has kept the greatest minds of our world on their toes. The answer is nestled in the heart of Einstein's theory of relativity, specifically the concept of a speed limit. Let's reverse gear for a moment and reflect the nature of speed. At its most straightforward, it's the measure of how swiftly one crosses the finish line in the race against time. Now imagine you're behind the wheels in this grand race. As you step on the gas, your car picks up speed. However, there's a line that it cannot cross. The car has hit its top gear, it's at its maximum capacity. The same rule applies to the grand cosmic race. As a competitor races faster and faster, edging closer to the speed of light, something unusual happens. The runner's mass gains momentum, an outcome derived directly from Einstein's ingenious equation, E equals mach squared. In layman's terms, the more vitality a racer possesses, the heavier they become. This mass gain poses a formidable challenge. It demands a surging amount of energy to maintain the pace. At one point, it would require an endless supply of energy to match or overtake the speed of light. With infinite energy not being an option in our cosmic marathon, the speed of light becomes a finish line that no one can cross. This doesn't assert that light speed is the ultimate speed. In fact, the cosmic stage, our universe, is inflating at an exponential rate, which, in certain aspects, can outpace light. But that's a story for another day. So why does light always win the cosmic race? It's not because it has an extraordinarily swift stride. It's due to the race regulations, the laws of physics as we comprehend them, that make it unachievable. As a competitor approaches the speed of light, its mass burgeons to a level where it would necessitate boundless energy to maintain the momentum. Hence, the speed of light continues to be the unbeaten champion of the cosmic race. So what does this all mean for us and our understanding of the universe? Let's take a step back and look at the big picture. The theory of relativity, as we've discussed, has dramatically altered our perception of the cosmos. It's a bit like we've been given a new pair of glasses, and everything we thought we knew has suddenly come into a much clearer focus. We've explored time dilation and the intriguing tale of the twins, a story that taught us time is not absolute. It can stretch and contract depending on how fast we move or how close we are to a massive object. This concept was unthinkable before Einstein introduced his groundbreaking theory. We've also delved into how gravity bends space-time. Gravity, as it turns out, is a distortion in the fabric of space and time caused by mass. It's not an invisible force pulling us down, but rather the Earth curving space around it that keeps us grounded. And let's not forget about the speed limit of the universe. The speed of light, a constant at roughly 186,000 miles per second, is the ultimate speed limit set by nature itself. Nothing can travel faster than light, not even information. And so, reside in a magical universe where time can stretch, space can bend, and nothing is absolute. Welcome to the world of relativity. As we conclude, it's time to pay tribute to the brilliant minds who have contributed to this video. This voyage through the cosmos has been presented to you by Newton Toe, a team completely committed to breaking down intricate scientific ideas into understandable and engaging content for all. The aim is to foster curiosity and instill an enduring passion for continued learning. A grand applause to our researchers, illustrators, animators, and of course our diligent scriptwriters for their relentless efforts to narrate this tale of relativity. And to you, our valiant viewers, for your consistent support and curiosity, we owe much gratitude. The universe is a boundless and intriguing space with endless opportunities to learn. Persist in your inquiries, continue your explorations, and above all, maintain the spark of curiosity and inspiration. A big thank you to everyone who has worked tirelessly and contributed to making this video possible. We are grateful for you. Until we meet again, this is Newton Toe signing off.